So phylogeny is about evolutionary relationships of organisms. And so one of the implications of evolutionary relationships has to do with similarities and differences between organisms. The more closely related organisms are, the more likely they are to share characteristics or traits, and the less closely related, the more differences there are in traits. So I want to refresh you on a term, homology. Homology refers to similarities due to shared ancestry. And so homology can be in traits or physical characteristics. They can also be in genes or molecular components of an organism. So a homologous morphology might be, for example, limbs in mammals. So if you look at a bat wing, a human arm, and a cat front leg, you see a very similar bone structure. And this is due to similarity because they have a shared ancestor. We can have homologous morphology among non-living organisms. So fossils, for example, let us see homologous morphology in the horse lineage. So that's a well-documented fossil record where we can see a lot of that. And then homologous genes are, again, same idea. The more closely related organisms are, the more similar their genes are going to be. And so this allows us to have percent homologies. So, you can say two organisms are 99% homologous or 75% homologous. And again, the implication is that the more homology, the higher this number, the more closely related the organisms are, and the more recently they shared a common ancestor. So one of the things we need to be careful with, though, is that in addition to homology, traits can be similar due to, or you can have analogous structures rather than homologous structures. So remember, the definition of homology is similarity due to shared ancestry. Analogy is similarity due to similar environments. To similar environmental pressures. Put that there. So similarity due to similar environmental pressures. So traits arise in two organisms independently, not because they got it from an ancestor, but due to adaptations to similar environments. So to kind of show you how this would look different in a phylogenetic tree, let me do kind of a silly example. So you have an ancestor who has two eyes. So those are my really bad eyeballs, okay? And then you have two descendants that also have two eyes, okay? So in this case, this suggests homology. The ancestor had two eyes and passed on that trait to its descendants. And so the two eyes trait is homologous in these two organisms. If this was an analogous structure, you would have an ancestor that had one eye, okay? And then you would have a different ancestor that also maybe had one eye, okay? And then you might have an organism over here that got two eyes, and this organism also got two eyes. Because everybody shares ancestry all the way back in time. If we went far enough back, these two ancestors also share an ancestor. But looking more recently, we see that the trait for two eyes didn't come from an ancestor that had two eyes that they shared. Instead, they both independently got the two-eye trait. They had a one-eyed ancestor. This individual now has two eyes. This individual had a one-eyed ancestor and now has two eyes. So they independently evolved the two-eye trait. That would be an example of analogous structures. And so whenever we're using traits, especially, this can be a little tricky. It can look like a trait's homologous, but if we start investigating a little bit more, it might become apparent that that trait is maybe analogous. And this, as we travel through the evolution of organisms like animals and things like that, we'll see many times like a trait is analogous. And so one example is sexual reproduction. Sexual reproduction will arise in many different organisms over evolutionary history, and it independently arises in many organisms. So we have different lineages of organisms that all evolve some different form of such sexual reproduction through convergent evolution. So analogy is due to convergent evolution. So a specialized type of phylogenetic tree is called a cladogram. And so we are oftentimes going to make cladograms in this class. And so a cladogram is going to show the proposed evolutionary history. So it's still a hypothesis. For our intents and purposes, we'll typically focus on traits. And one of the other differences with a phylogenetic tree is a lot of times in a cladogram, you might not know about the ancestors. You're just lining up modern organisms and proposing a route for how they evolved that way without actually filling it in with ancestor organisms, like without looking at fossils or things like that. So that's a little bit of a difference from phylogenetic trees, where a lot of times you're actually filling in ancestors that you know from the fossil record. So two aspects of a cladogram, or two kind of terms that we're going to use. There are shared primitive characters, or they're also sometimes called ancestral characters. So within the cladogram, we'll see traits that are shared by multiple organisms within the cladogram. And so it will be already present in the original organism or in the ancestor within that cladogram. So for example, if we have a cladogram like this, an ancestral characteristic or a primitive characteristic is going to be down here with the ancestor down here. They already have it. And then a shared derived character is going to be a trait where only some of the individuals within the cladogram have it. So for example, a shared derived character might arise here, and only these individuals would have it. So it's arising new within the cladogram. And cladograms are usually focusing on just a small number of organisms. So that's the other thing. It's just so everything we say about the cladogram is just for the organisms that are included in the cladogram. So also within a cladogram, we're going to see branch points. These are also called nodes. So again, this is a branch point here, a splitting into different organisms. And then a lot of times the reason why we're making a node is because there's going to be a difference. So for example, if I look at this one down here, I'm going to split there because I have some derived character or trait that's going to be different between these organisms and these organisms. And so that difference also creates what's called an in-group and an out-group. So again, this is just how you're looking at your cladogram. So if I'm saying that I'm going to focus on this trait in the trait arising there, then this becomes the in-group and this becomes the out-group. Or in other words, the in-group has the trait that you're interested in and the out-group does not have the trait that you're interested in. So if we look at this example, we have some modern organisms on here, some possible ancestors throughout the cladogram. And so this is within my cladogram, this is my oldest organism right here. And again, these are my newest organisms. And so if I want to know what the shared primitive character of D, E, F, and G is, then I'm looking for something that's already present in the ancestor. So one thing that's already present in the ancestor, for example, is 2 eyes. So all of them have 2 eyes. The ancestor had 2 eyes. So this was an ancestral or primitive character passed on to them. We could also say tail. That's another one. So it has a tail, and then that is passed on to everybody else. Okay, so again, that would be another primitive or ancestral character. The second part here is looking for a shared derived character of D and E. So we're focusing on D and E. So we're looking for a derived character, something that D and E are getting from their most recent common ancestor, but that this side of the cladogram does not have. And so we could maybe go with flippers. So we write in that trait here on the cladogram. And so one of the other things about a cladogram is we typically have traits written into them, and we'll see these throughout the semester. So ancestral characteristics are written down here, and then derived characters come into the branch points. So the presence of flippers arises in this ancestor and is passed on to D and E. D and E are now my in group. They have flippers. This becomes the out group. Okay. So that's the basic idea of how cladograms are going to work.